a lagoon. 150 million years ago, in what will one day be southern Germany, a chain of warm, shallow lagoons sits between low coral islands. The water is calm. The air is warm. Above the water, something is flying. It is the size of a crow. Its wings are dark, banded across the long flight feathers, and they beat in short bursts. 3, 4 wing beats, and then a glide, then 3 or 4 more. It is not a bird in the way a swallow is a bird. Its mouth is full of small, sharp teeth. Its hands still have 3 clawed fingers reaching forward beyond the wing. A long, bony tail trails behind it, feathered along its length. It banks slowly, and the sun catches the underside of one wing. There is a second row of feathers along the upper arm, long, soft, slightly drooping, filling the gap between the body and the wing the way a curtain fills the gap between 2 pillars. These feathers were not known to exist on this animal until 2025. They are called tertials. And what they mean is this. This animal was not gliding. It was flying. We have known about this creature for 164 years. We have called it the first bird since 1861. Its name is Archaeopteryx, which means ancient wing. And after a century and a half of looking at the same handful of specimens, the 14th one, the one in Chicago, prepared more carefully than any before it, has finally given us proof that this small, sharp-toothed, long-tailed, lagoon-skimming creature could actually do what its wings looked like they were built to do. It could lift itself into the air, on its own muscles, against the pull of the world. It is the oldest known bird in flight. And it is not flying alone. Somewhere not far away, in this same late Jurassic morning, an animal is browsing on the high fronds of a conifer. It weighs 45 tons. Its neck reaches 12 meters into the air. Its heart, to push blood up that neck, is the size of a small refrigerator and beats slowly and powerfully, all day, every day, for 50 or 60 years. The bird in flight, and the largest land animal that has ever existed. In the same epoch, in the same kingdom, descended from the same shared ancestor, 60 million years before. How did one lineage learn to make itself the biggest creature that has ever walked on land, while another, in the same forests, made itself small enough to leave the ground entirely? This is Cosmic Canvas. This is the Mesozoic. This is Episode 3, The Cathedral and the Feather. To begin, we have to return to the climate that ended the last episode. When we left the world, in the early Jurassic, 2 of the 3 main lineages of dinosaurs had just learned to carry their own warmth. The theropods and the ornithischians had become endothermic. They had walked through the Jenkins event, the hyperthermal climate crisis of 183 million years ago, and on the far side of it, they had moved into colder country than any large reptile had ever inhabited. The sauropodomorphs, the 3rd lineage, had chosen a different solution. They had grown enormous and let their own mass hold their heat against the night. The Middle Jurassic, roughly 174 to 163 million years ago, is a period we have few fossils from. The rock record is thin. But what we can see is that during this window, the climate gently cooled, Pangaea continued tearing itself apart, and both strategies kept refining themselves. They are sauropods. The lineage that was the size of a horse at the beginning of the Jurassic is now, in some species, beginning to push past 30 tons. Their necks have grown longer than the body. Their tails have become counterweights. They have stopped looking like animals and started to look like architecture. Meanwhile, in the other direction, the theropods are shrinking. Not all of them. The big predators are still big, but a particular branch of the theropod family tree, the Maniraptorans, are getting smaller. They are getting longer armed. Their feathers are getting longer, denser, more organized. By the end of the late Jurassic, a Maniraptoran can be the size of a crow, with feathered arms shaped like wings. This is the story of the late Jurassic. The same kingdom, the same forests, and two lineages running in opposite directions, harder than any vertebrates had ever run before. One toward the largest body possible, the other toward the smallest body that could still fly. We can follow them on 3 continents. In western North America, the rocks of the Morrison Formation preserve one of the most thoroughly studied dinosaur ecosystems in the world. Colorado, Wyoming, Utah, dated to between roughly 155 and 148 million years ago. The fauna is famous. Brachiosaurus, Diplodocus, Apatosaurus, Stegosaurus, Allosaurus. In southern Tanzania, the Tendaguru beds preserve a strikingly similar ecosystem on the other side of the world. The dinosaurs there have different names: Giraffatitan, Kentrosaurus, Dicraeosaurus, but they fill the same ecological roles. Giraffatitan is the African cousin of Brachiosaurus. Kentrosaurus is the African cousin of Stegosaurus. And in central Portugal, the Lourinhã Formation has produced a third version of the same fauna. 3 continents, the same animals, the same ecosystem. Because in the late Jurassic, Pangaea was still mostly intact. The Atlantic was a narrow seaway. Dinosaurs could walk from Wyoming to Tanzania with only the occasional swim. The late Jurassic is the last time in the history of the planet when the entire world's dinosaur fauna would look broadly the same. In the next episode, we will watch that unity crack apart. But here, in the late Jurassic, the world is still one stage. And on that stage, the cathedrals are rising. The largest land animal that has ever existed is something we cannot reliably name. The candidates are several: Patagotitan, Argentinosaurus, the fragmentary and controversial Bruhathcaeosaurus, and they all weigh somewhere between 50 and 100 tons by current estimates, depending on which bones survived and which scientist is doing the math. What we can say with confidence is that the largest land animal ever was a sauropod. And the lineage that produced these giants, the engineering blueprint that made 50-ton and 70-ton and possibly 100-ton land animals possible, that blueprint was built and tested in the late Jurassic. To understand why this matters, think about what it actually takes to be a 50-ton animal that walks on land. The largest land mammal that has ever existed was Paraceratherium, a hornless relative of the rhinoceros that lived in Central Asia about 30 million years ago. It weighed somewhere between 15 and 20 tons. The largest land mammal alive today is the African elephant, at 6 tons. The largest land animal that has ever lived in the entire 250 million year history of mammals is, in other words, between a quarter and a third the size of a mid-sized late Jurassic sauropod. Mammals cannot reach this size. They have tried. Paraceratherium, the largest proboscideans, the woolly rhinos, but every mammalian lineage that has approached 20 tons has hit a ceiling. The ceiling appears to be set by mammalian biology itself. The sauropods broke that ceiling by a factor of 3, then 4. Then they kept going. How? The answer is not one trick. It is a cascade of tricks, all inherited from earlier in the dinosaur lineage, all working together. Paleontologists have a name for the model that connects them: the evolutionary cascade for sauropod gigantism, formalized over the last 15 years by the paleontologist Martin Sander and his colleagues. It identifies 5 things sauropods had that mammals did not. The first is that they laid eggs. An elephant calf is born after 22 months of gestation, weighing about 1% of its mother's adult body mass. A sauropod hatchling came out of a soccer ball-sized egg after a few weeks or months, weighing about 1/100% of its mother's mass, which means a sauropod could produce dozens or hundreds of offspring across a lifetime, where an elephant might produce 4 or 5. Populations could rebuild fast. Individuals could afford to grow very, very large. The second is that they did not chew. Mammals process food in the mouth: molars that grind, jaws that move sideways, saliva that begins digestion. All of it expensive in skull architecture. Heavy jaw muscles, robust jaw joints, a brain pan that does not get in the way. Sauropods skipped all of it. Their teeth were simple pegs or spoons used only for cropping. The food went down whole. Digestion happened in a vast, slow gut full of microbes, which meant the head could be small, which meant the neck could be very long, because a long neck only works if the thing on the end of it is light. The third is that they had bird-like lungs. This one we saw last episode. The avian flow-through lung, with its system of air sacs, was already in place along the theropod stem, and also, separately, in the sauropod lineage. The air sacs extended into the bones themselves, hollowing them out, which is why sauropod neck vertebrae, despite being a meter long in some species, were strong but extraordinarily light. The lung extracted oxygen more efficiently than any mammal lung does. The air sacs may have helped dump body heat that would otherwise have built up inside such a large body. The fourth is that they grew fast. Very fast. A sauropod hatchling that emerged at about 5 kilograms had to reach 40 or 50 tons to be safe from predators. At a modern reptile's growth rate, it would take 1,000 years. It did not have 1,000 years. Fossil bone histology tells us that some sauropods, in their fastest growing years, may have put on 2,000 kilograms per year. They grew to adult size in 20 or 30 years. Fast for a 50-ton animal, almost impossibly fast given the engineering constraints. And the fifth, the one that connects all of these, is the high metabolism. The slightly elevated baseline temperature that the dinosaurs had inherited from their Triassic ancestors. In sauropods, that high metabolism powered the fast growth, ran the bird-like lungs, supported the population recovery that the egg-laying made possible. The sauropods did not become enormous in spite of high metabolism. They became enormous because of it. All 5 of these things were old. They had been built earlier in the lineage's history for other reasons. The late Jurassic was when they came together and produced the Cathedral. Stand in the shadow of a Brachiosaurus. The shoulder is 4 meters off the ground. The neck rises another 8 meters above the shoulder. The body is the size of a small house. It walks slowly through a stand of conifers, reaching up into the canopy that no other land animal can touch. It does not need to be aggressive or fast. It needs only to be there, slowly cropping the high foliage that nothing else can reach. Its heart, somewhere inside that vast chest cavity, is doing one of the most difficult jobs any heart in the history of life has had to do. It has to push blood up a neck 8 meters long against gravity every beat. The pressure required is enormous. The arterial walls must be reinforced. The whole circulatory system must be calibrated to keep blood reaching the brain without exploding the vessels in the lower body. This is engineering pushed to a limit the planet has never matched, before or since. And it is one of 2 stories happening in this same forest.
In the late 1970s, in the fossil beds of what was then called the Tiaojishan Formation in northeastern China, fossil hunters began finding something nobody had expected to find. They were finding small dinosaurs. Not the big ones we had known about for a century, but tiny ones. Crow-sized, pigeon-sized, lightly built 2-legged carnivores with long forearms and clawed hands. And preserved around their bodies, in the fine lake sediments of what had once been a quiet late Jurassic lake bed, were the unmistakable impressions of feathers. Not just downy filaments, real feathers. Veined, asymmetrical, organized into rows along the arms. The kind of feathers that, on a modern bird, you would call flight feathers. The animals were from about 160 million years ago, which placed them earlier than Archaeopteryx, the supposed first bird, by 10 million years. The most studied is called Anchiornis huxleyi, about 30 centimeters long, feathered arms and feathered legs, a tuft of feathers on the crown of its skull. And because the feathers were so well preserved, paleontologists were eventually able to reconstruct, from the microscopic structures called melanosomes in the fossil, what color it actually was. Anchiornis was the first dinosaur whose true colors we ever knew. It was gray along the body, with white and black banded wings and a russet-red crest on its head. A small black and white dinosaur with a red mohawk, climbing through the late Jurassic forests of China, gliding from branch to branch. It was not the only one. Within a few years, paleontologists had named Orornis, Xiaotingia, Eosinopteryx, Sericornis, a whole guild of small feathered theropods from the same Chinese formation. In 2025, a paper in Communications Biology by Josef Kiat at the Field Museum showed that Anchiornis already molted its feathers in a specific, organized pattern, the way modern birds do. The machinery of being a feathered animal, not just having feathers, but managing them across seasons, was already in place by 160 million years ago, before any animal we would call a bird had appeared. Then, 10 million years later, in the warm, shallow lagoons of what is now southern Germany, a slightly different animal appeared in the fossil record. Archaeopteryx, the ancient wing. We have known about it since 1861, when the first specimen was unearthed in a limestone quarry near the village of Solnhofen, just 2 years after Darwin published On the Origin of Species. Archaeopteryx was the proof. It was the missing link. Teeth in its jaws, claws on its hands, a long, bony tail, like a small dinosaur. Feathered wings, like a bird. Perhaps more than any other single fossil, it ended the 19th century argument about whether species change over time.
For 160 years, we had 13 specimens. We knew Archaeopteryx had wings, had feathers, had a head full of teeth. We knew it lived in or around the warm, shallow lagoons that became, in time, the Solnhofen limestone. What we did not know, definitively, was whether it could really fly. It looked like it could. The wings were asymmetrical, the way modern flight feather wings are asymmetrical. The bone architecture seemed consistent with active flapping. But we had never seen, on any specimen, the full suite of feather arrangements a modern flying bird has.
In 2022, the Field Museum in Chicago acquired the 14th specimen. When the museum's preparators began carefully working on the fossil, they used techniques earlier specimens had not benefited from. Ultraviolet light to reveal soft tissue impressions, computed tomography scans to read structures buried inside the matrix. The work took 2 years. The formal scientific description, led by the paleoornithologist Jingmai O'Connor, was published in Nature in May of 2025. And what they found on this 14th Archaeopteryx was something nobody had ever seen on an Archaeopteryx before. Tertials. A bird's wing, when extended, has 3 sets of flight feathers. The primaries, at the tip of the wing, the secondaries, along the forearm, and the tertials, the 3rd set, along the upper arm, attached to the humerus. The tertials fill the gap between the body and the rest of the wing. Without them, there is a gap behind the bird where air can flow through the wing in flight. With them, the wing surface is continuous from shoulder to wingtip, and the bird can produce real lift. The Chicago Archaeopteryx had tertials. Long, soft, slightly drooping feathers along the upper arm, filling the gap, completing the wing surface. This was the missing piece. Earlier specimens had not preserved them. The Chicago specimen, prepared more carefully than any before it, made the answer clear. Archaeopteryx had a complete flight wing. Archaeopteryx could fly. For 164 years, we have looked at this animal, debated this animal, written textbooks about it as the first bird. And only in 2025, in the literal lifetime of any reader watching this, did we finally see the feather that proved it. The first bird flew. We now know. And the kicker, the part that the O'Connor paper makes explicit, is that flight in the dinosaur lineage may have evolved more than once. Anchiornis and Aurornis and the other small feathered theropods of the Tiaoji Shan beds were probably not capable of true powered flight. They were gliders at most. But they had feathers. They had wings. They had the molting strategies of birds. They were assembling all the pieces. When Archaeopteryx finally lifted itself off a Solnhofen mudflat 150 million years ago, it was not the first feathered dinosaur to try to take to the air. It may have been the first to succeed. And it would not be the last to try independently. Within 20 million years, the Dromaeosaur lineage, the one that produced the 4-winged Microraptor, would experiment with its own form of flight. The transitions kept happening, in parallel, in different branches of the small theropod family tree. Feathers, once invented for warmth and display, kept being recruited for flight.
by different lineages, at different times, with slightly different solutions. There is a phrase the O'Connor paper uses, almost in passing. Flight evolved multiple times within the theropods. Read that sentence slowly. It contains an extraordinary claim. The architectural problem of generating lift from a wing, the most demanding aeronautical challenge any vertebrate has ever solved, that problem was solved, in some form, more than once, by different branches of the same family. The theropods did not learn to fly. They learned to fly several times. What is happening in the same forests, while the cathedrals rise and the feathers spread? Other things, too. The Ornithischians, the third great dinosaur lineage, are diversifying into shapes that have no modern analog. Stegosaurus, in the Morrison Formation, develops a double row of vertical plates along its back. Plates we now think were used primarily for display, possibly also for temperature regulation, but almost certainly not for armor. Kentrosaurus, its African cousin in the Tendaguru beds, takes a slightly different path. Narrower plates, longer tail spikes, smaller body. The Ornithischians are settling into the niches the sauropods cannot fill. The low browsers, the mid-sized herbivores. And the predators, of course, are doing what predators always do. They are getting larger to match the prey. Allosaurus fragilis is the most common large predator of the Morrison. 9 meters long, 1.5 tons. Long legs, lightly built, narrow skull with horn-like crests in front of the eyes. We know it hunted in groups when the prey was large enough to require it. The Cleveland-Lloyd quarry in Utah has yielded more than 50 Allosaurus skeletons concentrated in a small area, in proportions that suggest a death trap pool where animals went in and could not get out. In 2024, a team led by John Dennison reassessed the giant predator known historically as Saurophaganax. They reclassified it as a new species of Allosaurus, Allosaurus anax, possibly 12 meters long, the largest carnivore of the late Jurassic world. Alongside Allosaurus, the ecosystem held Ceratosaurus, with its horned snout, and Torvosaurus, an even more heavily built predator. The late Jurassic predator guild is rich. The herbivore guild is even richer. And underneath all of it, scurrying through the undergrowth, are the things we will become. The mammals. In every late Jurassic ecosystem we have studied, the mammals are there. They are small, nocturnal, unimpressive. Most are the size of a mouse or a shrew. They eat insects, seeds, small lizards. They hide during the day. They hunt at night. The dinosaurs do not pay attention to them. The mammals are too small to be food, too small to be competition, too small to matter. There is a temptation, when telling this story, to make the mammals into a kind of hidden hero, the patient lineage waiting for its chance. We should resist that temptation. The late Jurassic mammals were not waiting. They were doing what they did very well in the gaps the dinosaurs left for them. But they were there. And in 75 million years, the same circumstance that will end the cathedrals will hand them the world. It is 150 million years ago. Somewhere in what is now Wyoming, or Tanzania, or Portugal, pick any of the three, the scene is broadly the same. A single morning is unfolding in a late Jurassic conifer forest. A Brachiosaurus has been browsing in the canopy for several hours. Its head, 12 meters above the ground, has been reaching from one cluster of high needles to the next. It does not need to move quickly. The forest goes on for miles. The food does not run away. The animal is so large that nothing in this ecosystem can threaten it. In the canopy of one of the same conifers, a small animal moves. It is a feathered theropod, possibly an early relative of Archaeopteryx. About the size of a magpie, its arms are wings, its tail is feathered. Its forearm bones, strong, light, asymmetric in cross-section, are built for active flight. The Brachiosaurus reaches its head into the cluster of needles where the small theropod is perched. The small theropod, without panic, opens its wings, drops from the branch, beats its wings 3 times, and is gone. A flash of banded plumage between 2 trees, and then out of sight, climbing toward the next stand of conifers. The Brachiosaurus does not notice. It continues browsing. This is the moment that the late Jurassic gives us. The largest land animal that has ever existed, sharing a forest with one of the smallest. The descendant of the same 60-million-year-old common ancestor. One lineage gone enormous, the other lineage gone airborne. 2 strategies, the same kingdom, the same forest. Diverging from the same Triassic flicker of inner warmth in opposite directions, as far as opposite directions go. The cathedrals stretch toward the canopy. The feathers stretch toward the sky. And the world, for now, is wide enough to hold both. In the last episode, at the end of the early Jurassic, we said that the dinosaurs had finally learned to carry summer with them. This is what they did with it. One branch took the summer and built it into the largest bodies that have ever walked on land. 40 tons, 50 tons, possibly 100. Bodies that were themselves a kind of climate, that held their own warmth, made their own slow weather as they moved through the forests. The cathedrals of the Mesozoic. The other branch took the summer and pushed it in the opposite direction, shrank, grew feathers, then more feathers, then organized feathers, then asymmetric veined feathers, then wings. Then, at least once, possibly more than once, in different branches of the same family, actual powered flight. When we left the world in episode 1, the dinosaurs were nobodies, small and unimportant, waiting. When we left the world in episode 2, they had carried warmth into the cold. Now, in the late Jurassic, the inheritance has done its full work. The lineage has produced the largest land animals in the history of the planet, and it has produced the first animals that ever flew on muscle power alone. We are still piecing it together. The exact moment when powered flight became achievable in any one lineage, the gradient between gliding and flapping, is something we may never reconstruct in full detail. The fossil record is patchy. The soft tissues that matter most rarely preserve. But what is no longer in doubt, after the Chicago Archaeopteryx, is that powered flight existed in the late Jurassic. And what is no longer in doubt after the Tiaoji-Shan beds is that the lineage had been assembling the pieces for at least 10 million years before that, in multiple parallel branches. The cathedrals are gone now. The largest land animals ever to live are extinct. No mammalian lineage has come close to filling their space. But the other triumph is still here. There are, alive on Earth at this moment, somewhere between 10 and 11,000 species of birds. They are the most species-rich group of land vertebrates on the planet. They are, all of them, descended from a small lineage of feathered late Jurassic theropods that learned to take to the air. When you watch a swallow turning above a summer field, or a crow picking through a city park, or a hummingbird hovering at a feeder, or a hawk balancing in a thermal, you are watching the late Jurassic inheritance. Refined, miniaturized, perfected, but unbroken. The same wing architecture, the same feather grammar, the same hot blood. The same long-ago bet that the way to win at being alive on this planet was to be small and warm and lifted by air. The bet paid off. It is still paying off. In the next episode of this series, the world we have been describing, the unified global ecosystem of the late Jurassic, where the same dinosaurs walked from Wyoming to Tanzania to Portugal, will begin to break apart. The supercontinent will continue tearing. The Atlantic will widen. On the separated land masses, the dinosaurs will begin to evolve in different directions. The world will go global, which means, ironically, that it will stop being one world. The Cathedral and the feather. Both of them are inheritance. Both of them are the same story. One of them flew through it. This is Cosmic Canvas. Until next time.